All right, welcome to day 18 of assembly language class. We've spent all of our time so far, I think, talking about the 8086 processor or related topics. And that has set us up well for some of our next few topics where we get to talk about other instruction sets. One of them that you've been using probably since your first days as a computer scientist has been the instruction set that runs Java programs. Today, we'll talk a little bit about the Java virtual machine, including its instruction set and how the architecture works. And we'll see some things in common between that and the assembly language programs we can write on the 8086, and we'll later be able to contrast that with RISC instruction sets a little bit later. You probably know, and I know we talked about this a little bit in C class, that when you compile Java code, it doesn't compile, at least the plan for Java is it doesn't compile all the way down to native machine instructions. It compiles to this format called Java bytecode. That's kind of like an instruction set for a machine, but it's for a made-up machine. One that I guess, or at least originally, we never imagined we would build in hardware, but one where we could build a piece of software, a Java virtual machine, that could simulate that instruction set, a little program that knew how to simulate that instruction set. So once we compile a Java program down to Java bytecode, we can then run that bytecode on any machine that has, any host, any system that has a Java virtual machine that's been implemented on it. So we just have to compile it once to Java bytecode, and even though, at least informally, no real machine runs that Java bytecode, any machine that has a simulator for that Java bytecode, that has a Java virtual machine on it, can run that compiled Java program. You know from C class that many of you took last semester, C programs or C++ programs don't work that way. When you compile a C program, the compiler emits native machine instructions that run on a particular host. Normally they run on, or at least they're compiled to run on the system that you compile that code on. So when you compile a C program, you get, along with some other things, a big executable file that contains native machine instructions that run on that host's processor. Whereas, like we were just saying a slide ago, when you take a bunch of Java source code and run it through the Java compiler, you get out these instructions for a pretend machine, for a Java virtual machine. Fortunately, we can implement in software a Java virtual machine. That's down here at the bottom of this slide. We're pretending that's a little piece of software that knows how to read the Java bytecodes. And then for each Java bytecode, for each of these pretend machine instructions, it knows how to map that to instructions on the underlying hardware. And when I say it knows how to map that, that means it knows how to look at that Java bytecode instruction and say, oh, to do this thing, here's the sequence of real machine instructions I need to run. Now, there are some advantages and disadvantages of either of these approaches. Since C code gets compiled, and I know it says C++ here, I think these slides were originally from when students at NC State learned C++ as their first language. So it was natural to go from that to a lower level language. Most students going through the program now, they probably learned Java as their first language. And then you probably picked up C last semester in CSC 230. So when it says C++ up there, just pretend it's saying C. Most of this would be true for either of those languages. So when you have a C program, you compile it to instructions that are made for a particular machine. That includes a particular processor that knows how to run those instructions, or at least, sorry, a particular model of processor. And there could also be some operating system dependency. We saw a few lectures ago that the Calling conventions depend on the language and depend on the processor and on choices made by the OS designers. So even if you're running on exactly the same processor, you might have to compile C code to different executables depending upon your OS or depending upon your processor. So if you want to run it on a few different types of machines, you've probably got to compile that code multiple times, once for each machine you want to run it on. Again, because even if it's not just machine instructions, there are a lot of details about what's going on within that code that could depend on a lot of aspects of the machine. But for a Java program, we just have to compile it to one class file. We have to compile it to Java bytecode once. Sorry, I said class file a moment ago because that's the container for Java bytecode, among other things. We just have to compile it to Java bytecode once, and then that can run on any machine that has a Java virtual machine on it. This still doesn't free us from some machine dependence. Let me back up a slide to try to introduce this. Really, the fact that that JVM knows how to take Java bytecode that is kind of independent of particular platforms, and it knows how to do what that Java bytecode says on particular hardware and in the environment of a particular OS. Well, even if that Java bytecode is machine independent, that Java virtual machine is going to be machine dependent. We're going to need a different Java, at least a different executable, a different Java virtual machine program for every system we want to run Java on. And that's kind of what this slide is trying to show. If we want to run a Java program on 3 different systems with different OSs or with different processors, then we've got to take the Java virtual machine and we've got to build a version of that for one system and then build another version of that for different systems. So we still, even with Java, we've just pushed some of this platform dependency into the Java virtual machine itself. Now, Java bytecode may not depend on a particular platform, but the JVM still has to be compiled for every machine we want to run Java on. Well, is this as bad as what we had in C? We made the point before that, well, with C, every program you want to run might have to be compiled separately for every machine you want to run it on. Here, we have to do this with the Java virtual machine also. We have to have a working JVM for every machine we want to run Java on. But that's only the Java virtual machine. Once we've done that, once we've built a Java virtual machine for Mac OS running on Intel, and Linux running on Intel, and Linux running on ARM, and every system we might want to run it on, then we just have to, at least to run Java, we just have to build the JVM on all those different platforms. And then as many Java programs as we want to run can run on that JVM that we built. We made the point that the JVM might be dependent on the underlying processor. It might be dependent on the operating system. So we might need multiple versions of the JVM for every machine we want to run Java on. So how does this JVM work? We've made the point that it's a piece of software. It's a program that knows how to read in compiled Java and do what it says. So it's kind of like a processor. We spent a little bit of time learning how the 8086 works, and that includes understanding what its machine instructions are like, how they're encoded in memory, what kind of registers it has to work with. If we looked at the JVM like that, since it's running abstract instructions, since it's running made up Java bytecode instructions, what does it look like? How does it compare to something like the 8086? Well, it is a different way of describing machine instructions. It's a different way of writing a low-level program. If you look at the JVM and you look at the instructions it supports, it doesn't directly use CPU registers. So for 8086, we're accustomed to things like AX and BX and segment registers and instruction pointer and base pointer and things like that. And the Java virtual machine doesn't depend on any of those. At least its instructions aren't defined in terms of any particular registers. Instead, it depends on using a stack to compute intermediate results and to do things like pass parameters to return values. It has instructions, but usually those instructions are getting their operands off the stack. They might remove, and here's an example that might make this easier to describe. And it's the same thing we did with machine instructions earlier in the semester. If you wanted to do some high level statement like add what's in A to B and then store the result in C, in an 8086, we'd probably use some CPU registers to hold intermediate results and eventually store the sum in C. In Java, in the Java virtual machine, this is done on the stack. So over here is showing pretend JVM instructions that might do that kind of thing. We might get the value of A, push it onto the stack. We might get the value of B, push that onto the stack. And then the add instruction wouldn't require explicit operands. It would know that its job was to get its operands from the top of the stack. So when we do add, it would automatically pop the value of the top two things on the stack. So B and A that we just pushed onto the stack. It would add them up and push the result on the stack. So once these first three instructions are done, sorry, I realize I've got slides that help to show this. So let me finish saying this and then I'll go through and show the slides. When add adds these up, it pushes the result on the stack. And then if we want to save that, we can remove that value from the stack and store it in C. And like I said a moment ago, I should have been going through these slides as I was talking through this. Because when the first instruction executes, push A would get a copy of the variable A, what's in memory for variable A, store that on top of the stack. So we'll pretend the stack is growing in this direction. So just like the stack we used when we were talking about 8086, we'll pretend the top of the stack is always the lowest thing in this picture. So A gets pushed onto the stack, then a copy of B gets pushed onto the stack. And then, like I said a moment ago, instructions that compute things will implicitly get their operands off of the stack. So add will pop two values off the stack, add them up, and then store the result on the stack. And then, like I said a moment ago, if we want to save that somewhere, well, the result is left right there on the stack. So all we have to do is remove that or pop that off the stack and store it in C. Store it wherever we want to store it, which for this example, we're assuming is in variable C. So you can see here, the stack is really doing the job that we've previously done with registers. If you want to execute an instruction like add, you just need to prepare its operands on the stack. So a lot of the instructions that access memory are going to be transferring things to and from memory and the stack. And then the instructions that actually compute things are going to be accessing operands on the stack. I spent a long time describing that, partly because I probably did a poor job the first time. Any questions before we try to move on?
I'm curious why they designed it like this, because like you said, this is certainly a very different way of modeling machine instructions, and you'd think that it would be easier to map these kinds of instructions to existing processors if it was more similar to how those processors actually work with registers and instructions with particular operands and the like.
I think you make a good point. I've got a slide for that later that kind of argues, well, here's why this is a way that makes sense. To give two quick answers, just because the Java virtual machine, or just because Java bytecode uses instructions like this, doesn't mean they absolutely have to be implemented like this. So you could turn this into code that uses CPU registers more efficiently. I think the other thing I was going to say is, and the problem with mapping this to an actual set of registers is that might depend a lot on the processor. This is abstracted enough that it kind of defers the problem of saying, all right, when I say push something onto the stack, how are you actually going to implement that? Are you really going to push it onto a stack, or are you going to store it somewhere else? So I think this still leaves a little bit of room for optimization after the bytecode has been written, optimization in how that bytecode gets implemented or gets simulated during execution. Other questions I can try to answer? All right, so these are kind of pretend Java virtual machine instructions, just showing how you could use a stack as a replacement for what we've previously done with registers. A nice thing about this model is a lot of our CPU instructions get simpler. They even get shorter, or at least a lot of our instructions, even if they're not direct CPU instructions. So previously, if we were using registers and we wanted to add two things, we would have to encode an instruction that said add and then specified two operands. And you saw a couple of lectures ago, the way that's encoded in memory is a little complicated for, at least for humans. For the Java virtual machine, it's just an add instruction. It doesn't specify operands because it's implicit that, at least for add, the operands are going to come off the stack. And we don't have to have complex addressing modes. We learned about indirect addressing modes, like the one shown down near the bottom of the slide. And Java virtual machine doesn't have to do that kind of thing. If it has an instruction like inc, then it's going to increment something on the stack. And then if you want to get that from a location in memory, you're going to go get that and push it onto the stack before you even do the increment instruction. And if it takes some work to compute the location in memory where you want to get that thing, then you're going to have to do that work before you actually do the increment instruction. So having to put things on the stack, compute with them, and then leave results on the stack effectively breaks complex instructions like add what thing to what thing or increment something at this location in memory. It breaks those into multiple smaller instructions. And we just saw that something like add xy would effectively say, go get what you want for x, go get what you want for y, and then go add those two things. So individual instructions are going to be smaller and simpler. It just may take more of those to do what could be done with maybe a single instruction in 8086. Why favor this simple model of defining instructions and accessing memory? Well, the simpler we make the JVM, the easier it's going to be to target different architectures for that. And you've seen a little bit of this already. If I asked you about the x86, you would say, at least for the 8086, you would say, well, it's got a bunch of different registers. It's got 8 16-bit registers, and at least some of those you can think of as being 8 smaller 8-bit registers if you want to use them that way. And it's also got some segment registers for accessing memory. And it's got instructions that can only use particular or addressing modes that can only use particular registers particular ways. If you looked at something like ARM instead, and I think that's up for our next lecture, you'll see it's also got registers, but they're different registers. It's got 16, at least the 32-bit version of ARM has 16 32-bit registers, and 13 of them are general purpose. 3 have are special purpose registers like stack pointer or instruction pointer. At least that's the plan for how you're going to use them. So between these two architectures, there are big differences in what registers are available, what their capacity is, and what kinds of things you can do with them. If they defined the JVM to use registers instead, then how many registers should it have? If it had 12 or 16 registers, then it would probably be a lot easier to target it to something like ARM and a lot harder to target something like x86, at least efficiently. So here these slides are kind of making the same point. If you had to pick one of these two architectures, if you had to pick a particular number of registers for the JVM, that could restrict how easy it is to target a particular architecture, or saying things like the size of a register. By making it more abstract, it's easier to target a variety of hardware and say, come up with a JVM implementation that is as efficient as it can be on something like an ARM architecture and as efficient as it can be on something like an 8086 architecture. Sorry, I'm trying to figure out what I'm supposed to be saying for these slides. I guess here we're looking at different models for how we could execute machine instructions. So I'll try and read through this quickly. I apologize. I did read through this in preparation for class, but I kind of lost what we're talking about here. Thinking about different ways we can get the operands for an instruction. If we stored all operands in memory, then that's going to make, or if all operands had to be stored in memory, that's going to be slow. Accessing main memory is slower compared to accessing registers. Getting something out of a register can be much faster. And some of that simplifies our design for registers. Since they're already part of the CPU, you generally don't have to worry about caching what's in a register. You don't need extra. If you can keep all the operands in a register, then you don't have extra instructions to go load, to go access memory, load and store instructions to do that. So if you can keep everything in a CPU register, your code might look, if you can keep all of the data you're working with in CPU registers, your code might look like what's being shown here. Here, just accessing the contents of registers and storing the result in registers. If you have to access memory, then whenever you need to go get a value of one of these variables, or of A, B, C, or D here, or wherever you need to update a value, that's going to require access to memory. And that, in this small example, could make your code a little bit longer and a little bit slower. For Java virtual machine, where we're accessing where whenever we want to get an operand, we have to put it on the stack, and whenever we want to get a result, we have to get that off of the stack. That can result in what we said a moment ago, programs that are made of basically simpler instructions, but maybe a lot more of those simpler instructions, a longer sequence of instructions, to what we could do with a much shorter program if we directly had access to registers. Now, the JVM has more than just the ability to execute Java bytecode. There are various regions of storage in the JVM. And that's what this figure is showing. It's got, for running code, it's got a stack for operands. That's this part right here. And that's kind of what we've been talking about so far. As you're computing values, as you're computing a mathematical expression, you're going to be pushing values on the stack, using instructions to compute, to add or multiply values on the stack, and then getting results off the stack. So JVM instructions are going to be manipulating the stack heavily. Within a particular method, you also have access to multiple local variables. And that's what's being shown here. Each local variable has an index. So you might have local variable 0, local variable 1, and so on. And just like we saw when we were using the stack in 8086, there we might use the base pointer, and different local variables would be at different offsets from the base pointer. Here we've got kind of the same idea. It's just in a dedicated region of the stack for local variables. Each local variable, again, having an integer index that identifies it. So when you write your Java code, you might talk about a local variable named X. But if the compiler decides, oh, that's going to be stored as local variable number 0, if you actually look at your Java bytecode, it's not going to talk about a variable named X. It's going to talk about that variable's index in the array of local variables. So while a method is running in Java, it's using the operand stack to compute expressions, and it's using local variables to get values that it might push onto the stack, or to store results from the stack. Java also has, within the JVM, it's got code for all of the methods. So each time it has to load a new class file, it'll get the sequence of Java bytecode instructions for all the methods in that class file. And as it's running, it might have to allocate new arrays or new objects. And it's got a memory region for that called the heap. Same idea as heap memory in C. Whenever you call the new operator in Java, you might be allocating memory on the heap. And whenever the garbage collector reclaims some of that memory, it's putting it back as free memory in the heap. In a language like C, you had to manage heap memory yourself. In Java, you have to worry about allocating heap memory when you need it. But we usually depend on the garbage collector to reclaim that memory when we're no longer using it. Questions before I try to move on? So these are the main regions that Java bytecode can work with as it's running. And I guess I didn't say this part up at the start. The region of storage that is accessible to a method, we'll also call that a frame, just like we talked about a stack frame when we were talking about a function in C or in assembly language. And the frame of the currently running method would include its local variables and the contents of the operand stack. Instructions in the JVM are variable length. So some of them are 1 byte, some of them are going to be 2 bytes. Some of them could be longer than 2 bytes, but because individual instructions tend to be simpler than they were with 8086. We've made the point that an instruction like add doesn't have to include its operands, they're implicit. Then the encoding of an add instruction can be a lot simpler. All it has to do is say add. So individual instructions will typically be shorter to encode, typically 1 or 2 bytes. There are special, so normally instructions might have an operand, but there are special versions of some instructions that have shorter encodings for frequently used operands. What I'm really trying to say is the second bullet here. So you might have an instruction that'll let you get a local variable and push it on the stack. And there, which variable you want to push on the stack would be an operand of that instruction. But there would also be some specialized instructions that are made for pushing local variable number 0 or local variable number 1, just for the first few local variables. So for some instructions, there are optimized versions of these that include the operand, or where the operand is effectively part of the instruction. That lets us encode the instruction without a separate byte for the operand. It's all there in the instruction. And that's really what this second bullet says. I've probably done a poor job of saying it, but there are instructions to go get the value of your local variables. For most of those, which local variable you want is an operand. But if you want to get the first 4 variables, there is a dedicated instruction to do that, where the index of the variable is built right into the instruction. If you need a variable that's not one of the first 4, there's a version of the instruction that'll let you access that variable as a 1 byte operand. That would let you access 256 different variables. There's even a general version of it that'll let you have a 2 byte operand for which variable you want. That would let you access up to 65,000 different variables. It would take 3 bytes to encode that instruction, but for methods that needed a ridiculous number of variables, that could let them have an array of local variables with a lot of slots in it. So the point we're making here is shorter instructions are easier to load and can execute faster. So for accessing local variables, there are short forms of those instructions for accessing the early variables, longer ones for accessing a bigger set of variables, and even longer ones for accessing a really big set of variables. If we were executing a method that computed the same thing we were doing a moment ago, C equals A plus B. Well, if A, B, and C are local variables, then they would be stored in this local variable array, and that's what we're pretending this is. Let's say A starts out with a 10 in it, and B starts out with a 20 in it, and we want to add those two together and store the result in C. And let's pretend C is local variable number 2. There's a Java bytecode instruction, iload, that will go get a local variable. The I means integer. So go get a local variable that's of type integer out of local variable number 0, and load. Normally we would think of that as meaning load this from memory into a register, but we don't have registers. When we load something, it goes onto the stack. So iload is like a push. It goes and gets the contents of, well, for this instruction, local variable 0, and pushes it onto the stack. If we want to add 20 to that, the next instruction is going to say, go get local variable number 1, go get the contents of B and push that onto the stack. So iload 1 gets the value of B and pushes that onto the stack. And then to add these, the Java bytecode instruction for that would be iadd. That goes and gets 2 integers off the stack, adds them together, and stores the result on the stack. I'm going to back up a slide just so I can show that before we did the iadd, we had our 2 operands on the stack. When iadd was executed, it, as part of a single instruction, it removed those 2 things off the stack, added them together, and then pushed the result on the stack. Whereas these 2 iloads had an operand that said which local variable we're trying to access. iadd doesn't need an operand. It's implicitly going to operate on the 2 things that are on top of the stack. So it would get encoded with just 1 byte. Each of these, at least the way they're written down here, gets encoded as 2 bytes. And then if we want to store the result in C, that's going to be istore. That gets the integer off the top of the stack And as an operand, it expects which local variable do you want me to store that in. So if we're planning, or if the compiler is planning on storing C in local variable number 2, then iStore will pop a value off the stack and put that 30 in local variable 2. So like I said, if loads are really like pushes onto the stack, then stores are like pops, with the side effect of storing that value somewhere else. If we looked at this sequence of instructions as Java bytecode, it would look kind of like this. The load for A in slot 0, the load for B in slot 1, the add would be 1 byte, and then the store in slot, looks like a mistake in the slide. That iStore 0 should probably be a 2 to match what's up here. Questions before I say one other thing that is sort of a mistake. All right, remember several slides ago, like if you let me back up here, I was trying to make the point that there are special versions of instructions for accessing the early local variables. And this example didn't really show those. This makes it look like iLoad is going to take as an operand the index of the variable you want to load. And it can, but I think iLoad has a special version that says iLoad from 0 or iLoad from 1. There are only versions of iLoad like that for the early local variables, but it seems like this example is where we could have used those. That if there's a 1 byte version of iLoad that says just go get local variable 0, well, if we're only getting local variable 0, we could have used it there. Java bytecode, like the name suggests, the operand, the opcode for an instruction, is stored in a single byte. In fact, I didn't do a good job of saying it, but that was kind of implicit back here. The operator, the opcode for the instruction you want to do is stored in a byte. And then its operand, some of them might not need an operand. Some instructions might have a 1 byte operand, and some instructions might have a 2 byte operand. So if each opcode is a single byte, that means the Java virtual machine can support up to 256 different machine instructions, each one with a specific 1 byte code that says what that instruction is. So the instruction iLoad that we were just talking about, there's a bytecode for that. The iStore instruction or the iAdd instruction, there's a bytecode for that. There are bytecodes for pushing particular, well, we just said there are bytecodes for pushing some of those low-numbered local variables onto the stack. There are bytecodes for pushing particular constant values onto the stack. Like if you needed 0 as an operand in a computation. Well, fortunately, if you want to compute with a 0, you have to get it onto the stack. And fortunately, there's a bytecode that says push a 0 onto the stack. In fact, for a bunch of small values like 1, there's a Java bytecode that says just push a 1 onto the stack. Or -1's pretty useful, just push a -1 onto the stack. Or 2, or 3, or 4, or 5. For each of these instructions, when they were designing Java bytecode, each instruction they want to have like this, an instruction, a dedicated instruction that says push a 4 onto the stack. They're using up one of these 256 available instructions. When they were designing Java bytecode, they tried to spend those 256 instructions or 256 different codes as carefully as they could to try to minimize the complexity, minimize the length of programs you might write in Java. We can look at how we could look at every individual instruction. It would take several slides just to show them. But here we're looking at them in big groups. There are 256, or at least we got room for 256 instructions. Of those, about a third represent pushing local variables onto the stack. So a lot of those are just used for getting local variables, getting the contents of a local variable onto the stack. There are, and those would be the load instructions. There are store instructions, so they would pop a value off the stack and store it somewhere. But those are only about 7% of the instructions. So a lot more instructions dedicated to getting operands on the stack, and a lot fewer to getting results off the stack and storing them somewhere. Now, the example we just looked at shows some of why this is true. There are a lot of different things you might want to use as an operand when you're computing that don't have corresponding store instructions. That's what we were just talking about. It makes sense to have an operand that says push a -1 onto the stack. That would be for loading something onto the stack, but there wouldn't be an equivalent store instruction. There's no meaningful operation to get something on the stack and store it as a -1. So for pushing, say, constant values on the stack or other fixed constants on the stack, so I guess constant numeric values or other types of constants, we would have a lot of push operations without corresponding pops. Same thing for accessing stuff in memory. I guess we were just talking about this example of pushing constant values onto the stack. About 10% of the, and I'm just looking at this table here, about 10% of the Java instructions of those 256 bytecodes are for doing mathematical computations. About 8% of them are for branching, for conditional execution. A little bit fewer, about 7% for calling methods and returning from methods. And then some other operations for things like stack manipulation. I know there's one that'll take the top 2 things on the stack and will reverse them if you need to change the order of something on the stack. So there are some operations just for working with the stack without necessarily pushing stuff onto it or computing stuff from it. So the operand stack is used to do computations, backing up a couple of slides, a bunch of slides for this, for things like this, for just computing the value of an expression and storing the results. It also has to have mechanisms for calling subroutines, for calling methods, and returning values from methods. Internally, this is also done using the same stack operations, just like, so the Java stack that is used for computing stuff is also used for staging parameters for a method call. And this is kind of like what we saw when we were calling assembly language code from C. If you're running a C program and it calls a function, it pushes the operands on the stack. These same stack manipulation operations are used in Java to stage the parameters to a method that you want to call. So within a method, you have access to your local variables. You have access to an operand stack that you can use for computing new values and for pushing parameters to other methods that you want to call. And we were describing this kind of like a stack frame in an assembly language program. If you had a stack frame, you could access all of its elements using, well, in 8086, we would access elements of our stack using something like the base pointer. And in one direction from the base pointer, we could access parameters passed to a subroutine. And then if we wanted to call our own subroutine, we would push parameters for that one onto the stack. Java virtual machine does the same thing. So if you want to call another subroutine, you push the parameters for that onto the stack. And when that subroutine wakes up, those parameters are going to show up in local variables for that subroutine, just like you expect in a C program. So if you're writing in C, you can declare as many local variables as you want, but any parameters that you were passed show up just like local variables. You can access them the same way as local variables, and they're also stored on the stack, just like local variables. And that's what we're trying to show here. So if while you're executing a Java method, you're about to call another method, you stage parameters for that method on your operand stack. And then when you call that method, it expects those parameters to show up as local variables in that method. Well, we could copy, whenever we start that method executing, we could copy those parameters over to the local variable array for that new method, or we could just let it use that section of memory as the start of its local variables. And to make Java more efficient, that's how it can be implemented, just like we did in assembly language. The caller is using, or the caller can use stack memory. They can use their operand stack to compute values, to stage parameters for methods they want to call. And then when those methods start executing, if they use the top part of their caller's operand stack as the first part of their local variables, then they can automatically access those parameters that were passed to them, along with any other local variables they need to store. And then they can use additional stack space in this same stack to do other computations or to stage other parameters to methods that they might call. So even though Java is described with an abstract machine, it can still be implemented using some of the same kinds of techniques that we use with 8086. I added one new thing to the slides, and that is the Java P command. You may have never used this, but you probably have it installed. When you install the Java Development Kit, you get a small collection of utility programs that are awfully handy for looking at Java programs, either running Java programs or just looking at Java class files. And Java P is one of these. It's probably, if you installed the Java Development Kit, you've probably already got it. And it's kind of like a Java class file disassembler. It takes a few different options. But if you run it with the -C option, it'll show you the contents of a class file. So you can run it like I'm showing down here, Java P, and then -C as the option, and then any class file that you've built. I think you can even do this with class files from the built-in Java API. And it will show you the contents of that class file. And with -C, it will show a disassembly of each method in that class file, disassembling it to Java bytecode. I can only fit a little bit of this on the slide, but this is showing the sequence of bytecode instructions for a little hello world program I wrote. So this is the main method in that program, and it takes an array of strings as its parameter, just like you'd expect. And then just to make it more fun, I concatenate the strings hello and world. And I wrote this in plain old Java, and then I compiled it down to a class file. And this is looking at what it got compiled to. So this LDC is for load constant. That's getting the hello string that I defined and pushing it on the stack. And this is storing it in local variable number 1. I'll show you one thing. For this LDC, there's the instruction. That's the opcode, and that's the operand number 2 for this instruction. This is one of those efficient store instructions. Remember we said, well, for accessing low numbered local variables, Java bytecode has defined some operands that include, some opcodes that include which local variable right in the opcode. And that's what you're seeing right here. A store _1 is an instruction that's made for popping I think that's for an address A off the stack and storing it in local variable 1. And then we won't read through the whole thing because this is just a tiny bit of it, but then we get another string and that goes in local variable 2. And again, there's a short version of the store instruction, provided you just want to store something in local variable 2. If you want to see larger or more realistic examples of what you could do with Java bytecode, this command will let you see a disassembly of any Java bytecode method that you want to look at, which can be, again, kind of fun to take a look at. Questions before we move on? We made the point before that, well, since Java is compiled down to a made up instruction set, to Java bytecode, that's going to hurt performance a little bit. At least it could it could slow down execution, because instead of that instruction running natively on a processor, we've got to have a little piece of software that knows how to run each of the potentially 256 bytecode or instructions that have a bytecode. That would mean that Java virtual machine has to over and over do what the processor does in hardware. It has to go fetch the next instruction, figure out what that instruction is, and then do what that instruction says. When we build this into hardware, well, for a lot of instructions, this can be built so that all of that is done in a single clock cycle. But if we have to do this in software, it might take a few machine instructions to go get the next bytecode, and then maybe a bunch of machine instructions to figure out what that bytecode is, and then even more machine instructions to do what that bytecode says. So this could slow down execution by a factor of 10 or a factor of 100. Because of this, people have tried to be creative in how they implement a Java virtual machine, and they've come up with some clever options for how they can implement a JVM so that it can execute Java bytecode really quickly. The obvious way is kind of what we've been talking about so far. We just need to build a piece of software, a little program that knows how to do what the JVM is expected to do. It has a heap and knows how to allocate heap memory and run a garbage collector. It knows how to allocate space for a stack that we're going to use to store local variables and operands and parameters for any calls we need to make. And it knows how to run every Java bytecode. It knows how to do every instruction that has a Java bytecode. Once we load in a class file, its job will be just to go get the next JVM instruction, execute it, and repeat. So over and over, it'll be fetching the next instruction, figuring out what it says, doing what it says, and then going back and getting the next instruction, just in a little tight loop, simulating what a CPU might do in hardware. Running instructions over and over in that loop, it'll be doing the same thing to run instructions, although as instructions are run, that'll change the contents of the stack, that'll change what's in the heap, it'll change other parts of the JVM as the program runs. Since every instruction might take multiple steps to run it in software, this could be slow. We could try to make this a little bit faster by reducing our dependence on I/O. Instead of loading class files from disk, or at least instead of loading stuff from disk every time we need to run it, we could load it into memory, decode some of the instructions, and then leave them in that decoded state so that we didn't have to repeat that computation every time we ran that instruction. That could save us some I/O operations and some work decoding instructions. But it's not going to be as fast as running native code. How about if we tried to do what a C compiler does? Could we compile Java source code all the way down to native machine instructions? And the answer is yes, and it's been done, but it hasn't been done a whole lot. There are Java compilers. In fact, I think GNU had one until recently that would compile Java all the way down to native machine instructions. If you did that, you would really be doing it in the interests of speed. If you can take a Java program and compile it down to native machine instructions, then you're going to run at processor speeds rather than at interpreter speeds. But you're going to lose a lot when you do that. Your code, if you compile it all the way down to native instructions for every method, it's not going to be portable anymore. It's going to be tied to that particular hardware. And a lot of the JVM, a lot of the overhead of the JVM doesn't really have anything to do with running native instructions. It's due to other parts of the JVM. The JVM is always running a garbage collector, and even if you can run Java bytecode really fast, that garbage collector is going to have some overhead. Also, because as you're running a Java program, you're always loading in new class files. That can make a program harder to optimize because you don't have all of the code at once to look at. For a language like C, since you compile each file separately and then you link everything together at the end, you at least have a point where you have access to all of the code and you can make some optimization decisions that you couldn't make if you didn't have access to all of the code at once. This approach, of course, if we can compile down to native instructions, then it could at least make our JVM a lot faster. Instead of having to have a piece of software that did the fetch, decode, and execute of every instruction, by compiling down to native machine instructions, we'd be getting the processor to do that for us. Again, though, we said you'd still have a fair amount of overhead because the definition of the JVM still requires using a stack, for instance, and replacing the use of registers with stack operations can still have a cost in terms of performance. So like I said, this has been done. It doesn't appear to be very common, and even the GNU project that compiled JVM or Java all the way down to native instructions doesn't seem to be being maintained anymore. So what else could you do? Well, a very common approach, in fact, so common that modern JVMs do this all the time, is instead of just depending on software to simulate every bytecode, we could, well, let me try introducing this again. We could use what's called just-in-time compilation. Again, instead of simulating every bytecode, how about when we first run a method that's part of a class, we convert all of the code of that method into sequences of native instructions that do whatever that sequence of bytecode said to do. So if we see a, say, an iload instruction, we could write out native machine instructions that go get something out of one part of the stack and copy it to the operand stack. So it can be used as an operand or a parameter for the next instruction. And if we do that for the entire method, so we go through all the Java bytecode for that particular method and convert it to equivalent sequences of machine instructions. Now that'll take a little bit of time to do that conversion, but if we save the converted instructions, the next time that method is called, we can just run the natively compiled version of that method without repeating the conversion. So the first time we call a method, there's going to be a little extra work to compile it the rest of the way down to native instructions. But every subsequent execution could be a lot faster. And we could even pick and choose which methods get compiled down to native instructions. Methods that are short and called a whole lot, it makes sense to compile those down to a short sequence of native machine instructions. Instructions that are rarely used, there's probably no point doing this, since the overhead of compiling them down to native instructions might dominate the savings on that. So within a particular class, some of its methods could get compiled down to native instructions, and others wouldn't have to be. This has an advantage. So backing up, this just-in-time compilation has an advantage over compiling to native machine instructions at compile time. Just-in-time compilation has the advantage that it maintains portability. Your class file still just consists of Java bytecode. It's just as you start running methods in that Java bytecode, the JVM, or sorry, in that class file, the JVM might choose to natively compile some of those methods if it notices that they're getting used a lot. For each method that gets compiled to native instructions, it could run a lot faster. And like I said, we wouldn't even have to do this with all the methods. We could just do it with the ones that are getting called frequently. In fact, we could even compile different versions of a method based on how it's used. Down at the bottom, we're showing how this might apply to 8086 instructions. If you had to double a value like X, you might be able to do that efficiently, so multiply it by 2. If you just had to double it, it might be easier just to add a copy of X to itself. Or if X was a constant, it might be easier just to pre-compute the value of that constant doubled. And if we can have multiple different compiled versions of a method, we could call the fastest version of that method based on the parameters that we're passing to it. So like I said, this is probably the most popular approach for implementing a fast Java virtual machine to compile methods from Java bytecode to native instructions, but to do it while the JVM is executing rather than doing that for an entire program when you're first compiling it. There's another way we could go, and this was popular in the early days of Java, but maybe not as popular, or apparently not as popular now. We could build a processor that we could build a processor in hardware that just knew how to run Java bytecode. Earlier, I said Java bytecode is a made-up instruction set that no real processor runs. But that was a little bit of a lie. There have been processors built in hardware that know how to run Java bytecode. The advantage of that is they could be a lot faster than the process of fetching instructions and decoding them could be done in hardware rather than having a little program that knows how to do that. So this could be faster than doing it in software, but it's going to require special purpose hardware and hardware that was made just to run Java bytecode is going to be less general purpose. This has been done a few times. There are some efforts to do this, but it doesn't seem to be as popular as it was in the early 2000s. I think partly because other technologies like Java or just-in-time compilation have yielded pretty fast executing Java, or Java virtual machines that are pretty fast without having to build dedicated hardware that's made just to do that. Like I said, if you're interested in this kind of thing, I would encourage you to try out that Java P program that I mentioned before. It should let you look at the Java disassembly of any code that you write and see what's going on within it. That's all I've got to cover for today. It's a little bit of a short day. I'll take questions if people have them, and I'll hang around once I stop recording. Any questions while we're still recording? All right, stopping the recording.